saw in last class the point form of Gauss's law. If you recall, the point form of Gauss's law introduced us to a new operator called divergence. This is the point form of Gauss's law, which is given by del dot D equals rho, rho being the charge that is enclosed or that is charge that is present at a particular point. D is the electric flux density, and this del dot D expresses the vector operation of divergence. So, let us look at couple of examples of this divergence or how to calculate divergence, and then we will move on to interesting things. Consider, for example, that I have vector field D, which is the flux density D, given by some constant times z hat, indicating that this electric field is constant and it is in the direction of z hat. It is completely independent of x, y and z positions. So, if I ask you to evaluate the divergence for this particular vector field, how would you proceed? You would recognize that this is in Cartesian coordinates, simple to recognize that one, and then you can use the formula for del dot D that we developed in the last class, which is given by del x of dx plus del y dy plus del z dz, and then substitute for the corresponding components dx, dy and dz. In this case, you do not have dx component, you do not have dy component, the only component that is present, that is non-zero, is dz component. And what is the value of dz? Dz is equal to k, where k is a constant. K is a constant. Okay. So, you now take del dot D, which is essentially evaluating this particular partial derivative del z of dz, and if you do that one, you are going to see that since dz is constant, its derivative will also be equal to 0 with respect to z, and therefore, you get del dot D is equal to 0. If, for example, this particular field D field would have represented field because of a certain charge distribution, what is the meaning of this del dot D being equal to 0? For that, you try to sketch how the D field itself would look like. Now, the D field is along the z direction. So, let us mark the x, y and z directions on this paper. So, you have y, x and z, and at all points x, y and z, the vector field D is directed along z axis and has a constant value of k. So, it could be written by giving constant k values, okay, at all points. So, you have at all points the vector field D being given by the constant value of k and headed in the direction of z axis. So, as you can clearly see, if I take any volume over here and then evaluate what is the flux lines that are coming out of this surface, the surface is bounding this particular volume that I am showing here. So, there is a D field coming out of the surface. If you try to evaluate what is that integral d dot ds over this set of surfaces which correspond to a particular volume, and then take or divide the corresponding value by delta v, this is the closed surface, and then let delta v go to 0, you will see that this particular quantity will be equal to 0 simply because the numerator is equal to 0. There are as much flux lines that are entering this surface as those flux lines that are leaving this surface. If you want, you could try this one in cylindrical coordinates, and you would recognize that that statement is true regardless of your working in Cartesian or cylindrical coordinate systems, right. So, you could see that in this surface which I have taken here, the corresponding value of this integral d dot ds will be equal to 0, because on the top surface you have some flux lines coming out, whereas from the bottom surface there is as much flux that is going in. So, there is a balance of the flux going in and flux coming out, which makes a numerator 0, and then when you take this ratio of this, when this essentially becomes equal to 0. In other words, the fact that del dot D is equal to 0 indicates that the corresponding point where you are evaluating the divergence, okay, or you can imagine a very small volume around this particular point, it contains no sources. Here the source for D field is charges, therefore, it contains no charges. So, at any point where the divergence vanishes, it simply means that there is no charge enclosed in that volume. Okay. So, you can take that small volume and see that there will be no charge enclosed. Now, that is the meaning of del dot D equal to 0. Let us get a little more adventurous and try to evaluate the divergence for a point charge. We know that for the point charge, the D fields would all be in radial direction, correct. Let us say the point charge has a value of q. So, the D field will all be in the radial direction, and this value of the flux density dr at any particular point r or at any distance r from the origin will be given by q by 4 pi r square, right. It is varying as 1 by r square. Now, you imagine that I am going to put a small volume. Let us actually try to put a small sphere at any point, okay, not at the origin. See, the charge is placed at the origin, but my Gaussian surface that I am placing, which encloses a volume which is essentially a sphere, I am going to place this one at some other point, okay. And then you can see this, I am not going to derive this one, but you can see that on this surface the D field will be perpendicular to the surface, right. So, perpendicular to these 2 points, and at these 2 points there is as much flux that is going in as much flux that is coming out. Of course, you do not want to take a large sphere that would be like this, right, because the D field over here will be different from the D field over there, yet you would still show that if you start shrinking the volume of this sphere by letting its radius go to 0, the corresponding point, that is at this point, del dot D will be equal to 0, okay. So, del dot D is equal to 0 at any point, okay, that is not at origin. So, this is the statement that we just made, that if your volume does not enclose any point charge, then value of divergence will be equal to 0. Now, you might ask, what if I do not consider this at any point not from the origin? What happens if I take this sphere around the origin, where I know that there is some charge enclosed, okay. Let us also call this radius of this small sphere as small r. I hope that there will not be too much of confusion here. So, I am taking the sphere r, which is now centered at origin and has a radius of r. Eventually, I am going to consider this radius r go to 0, so that I can obtain del dot D at the origin. So, I want to find out del dot D at origin, okay, by placing a sphere of radius r around that origin, okay, and then letting that radius r go to 0, so that I can approach del dot D. Now, you could do this problem by looking at textbook and then finding out what is the corresponding formula for del dot D, okay. There are formulas for divergence in spherical as well as cylindrical coordinate system that is typically given in textbook. You can do that. However, let us go back to the definition of divergence and see what would this del dot D turn up to, okay. Remember the definition of del dot D at any point. The definition of divergence at any point was the closed surface integral D dot S, where that surface S encloses that particular volume, divided by the volume element itself, and then letting that volume element go to 0, okay. Now, I know that D field for point charge goes as 1 by r square, right. So, the D field decreases as 1 by r square. Therefore, at the surface of the sphere, which is at a distance r, or it is at a radius r from the, as measured from the origin, will be q by 4 pi r square, okay. This needs to be multiplied by the surface area of the sphere, because D field will be everywhere perpendicular to the surface, and therefore, that integral of D dot ds simply becomes multiplying the value of D with the surface area of the sphere. So, when I do that one, and I know that the surface area of the sphere of radius r is 4 pi r square, I see that D dot ds, that is this integral of D dot ds over the sphere which is having a radius r, will actually be equal to some constant, and this constant value is q, okay. Now, this is not the end of del dot D, this is just the numerator part of del dot D that we have obtained. Now, if you look at what is the volume element, or what is the volume of the sphere of radius r that we have, the volume is given by 4 by 3 pi r cube. I hope that these formulas are familiar to you. If they are not familiar, you can consider this as exercises in evaluating the surface and volume integrals in spherical coordinate system, and you can find this out. So, coming back to this, the volume that is occupied by the sphere of radius r is given by 4 by 3 pi r cube, okay. Now, del dot D will be over that sphere now. See, I am not looking at del dot D at the point as of now, because I have considered a sphere of radius r and I have not yet let r go to 0. Okay. Now, to obtain the divergence at a point at origin, I am going to let the volume element go to 0, which is equivalent of letting r go to 0. Okay. If I do that, this is equivalent of the same thing. So, if I do that one, then numerator is constant q, denominator has some 4 by 3 pi r cube, and as r tends to 0, what happens to this quantity in brackets? This quantity just shoots up to infinity, right. So, the conclusion is that del dot D goes to infinity. Now, this is mathematically alright, but physically this is not correct. Okay. The reason why this is happening is because we assumed the charge q has no spatial extension, and essentially what we were trying to do was to give that value of r, which is in this particular denominator for the for the flux density, equal to 0. So, if we try to set r equal to 0, the field of the point charge at the point charge location itself blows up to infinity, right. See, in earlier cases we never went so close to the point charge, but now we are trying to find the field at the location of the point charge, which simply means that this D field essentially goes to infinity, it just blows up to infinity. So, this is clearly unphysical result, and to deal with such unphysical results, mathematicians have introduced and physicists have extensively utilized this tool called delta functions. Okay. A delta function is something that shoots up to infinity at a particular point. However, the area of that function under, if you integrate that one, that would be equal to some finite value. Formally, you define delta function at any point, say x, as this quantity. Okay. So, when you integrate from minus infinity to plus infinity, and then delta of x dx is equal to 1. In practice, you can approximate this delta function by considering pulses, okay, of any shape that you want, but their amplitude keeps on increasing. So, you can actually you can approximate this delta function by considering a sequence of pulses whose amplitude keeps on increasing while its width keeps on decreasing, so that the area under this pulse or this curve would always be equal to some finite value. This is called a delta function, and in terms of this delta function, you can show that the divergence of D field at the origin will be given by q by 4 pi r square. Okay. If you just leave it like this, obviously this is going to go to infinity at r equal to 0, which is the origin where the charge is kept. Therefore, you multiply that one by delta of r, okay, and you will interpret this result as saying that if you integrate this del dot D over the volume, that fellow will be equal to 0. That is, if you take the integral of del dot D over the volume, which is equivalent of considering integral of del D dot ds over the sphere of radius r, that will not be equal to 0, and that will actually be equal to the amount of charge q. Okay. So, if you integrate this del dot D over the volume, okay, or equivalently integrate this d dot ds of the point charge with this divergence given up here, this will be equal to the total charge enclosed, which happens to be the point charge q. At any other points, if you try to evaluate the divergence, that divergence value will be equal to 0. Please note that divergence is related to the corresponding volume or the surface that you are choosing. Okay. It is possible to choose a different type of surface. Okay. However, the evaluation of the D field in any arbitrarily chosen surfaces is going to be difficult and not usually recommended. Okay. So, let us just review back what we said. We started with the point form of Gauss's law, okay, and we considered two examples of calculating the gradient. In the first example, D was equal to some constant directed along z axis at every point in space. So, if you try doing the divergence at any point, this would be equal to 0, because the volume or the surface would not enclose, the volume actually would not enclose any charge. There is as much flow of flux lines into the volume as there is a outflow of the flux. That was the first example. In the second example that we considered, we had a point charge placed at the origin whose field decreases as 1 by r square. So, if you try to consider sphere which is at any other location than the origin, then the corresponding del dot D value evaluated at that point will be equal to 0. So, at any points not at the charge itself, the divergence will be equal to 0. However, the value of the divergence at the point goes up to infinity. We accommodate that infinity by defining a function called delta function. Okay. Let us consider one additional example of divergence, and we will wrap this divergence up to introduce you to another vector quantity. So, let us try to calculate, or let us try to evaluate this d dot ds over a surface that I am going to give you now. So, I want you to evaluate the total flux that is coming out, integral of d dot ds over a cylindrical surface, okay, of radius a and a height h. Okay. So, I consider a cylindrical surface of radius a and a height h, where the d field, okay, the flux density is given by r. What is r? R is the position vector. So, if you take this as the origin, r is the position vector. So, at the surface of the cylinder, which is at this point, the corresponding value of d will be equal to a. This will be a times r hat. R hat is the unit vector in the radial direction. So, this is the vector that I am going to consider. So, a times r hat plus z hat, where z is this height z. Okay. And on this surface you need to find out what is d field. Of course, d field would also come out of the top and bottom surfaces, and you would need to find that also. So, if you just sketch how the d field would look like, this is how the d field would look. Okay. At each point it is going to be a vector. Okay. Although I am showing you vectors of different magnitudes, they are not actually different magnitudes, they would all be of the same magnitude up here. Okay. So, this is how the d field would look if you try to find this one on the surface. Okay. So, at each point on the cylindrical surface, you have to break up that vector r into two vectors, one vector along the radial direction and the other vector along the z direction. Okay. One vector along radial direction and one vector along z direction. So, you have to break this vectors all up. Okay. At the top surface, this particular line will always be along the z axis, this line will be along minus z axis. Okay. So, to evaluate this integral of d dot ds over the cylindrical surface, closed cylindrical surface that I am considering, I need to first express the electric field at the surface. So, now this cylindrical surface has three surfaces in itself, right. There is a curved surface, there is a top surface, and then there is a bottom surface. On the curved surface, the surface element ds is directed along the radial direction. So, dsr is equal to a d phi dz, because r is equal to a, the radius. On the top surface, the surfaces are directed along z axis, that will be given by d r d phi a. At the bottom surface, the surface element would be directed along minus z direction, and that is given by minus a dr d phi with appropriate integration limits that you need to consider. Okay. So, on the curved surface, we have the value of d field being given by a r plus z z hat. So, the integral of d dot ds on the curved surface becomes integral of, only the r component will be there, because on the curved surface the surface element is directed along radial direction. Therefore, this will only be the r component that would be non-zero here on the curved surface. And what is the r component of the d field? It is a, right. So, you will have a square d phi dz, and the integral is over phi is from 0 to 2 pi, and integral of z is whatever the height of this d field h. Okay. So, you could consider, for example, this to be from minus h by 2 to plus h by 2, so that a total height of the cylinder is h. And if you look at what is this, this would be 2 pi a square h. Okay. So, this is one partial result that you can keep. The other results are the top and bottom results. For the top, the d field is directed along z axis, right. I mean, the d field has z components along positive z direction, and the integral of d dot ds on the top surface is given by h into a d r d phi, right, where phi goes from 0 to 2 pi and r goes from 0 to a. So, if you evaluate this integral, you are going to see that this integral will be pi a square h. Similarly, for the bottom integral, you have integrals from 0 to a, 0 to 2 pi, okay. H will be h. However, the value of d component on the bottom surface is directed along minus z direction. Therefore, this will not be h, this would be minus h, but the surface element is also directed along minus z. Therefore, I have minus a dr d phi. There are two minus signs which can be eliminated because it becomes 1, and if you evaluate this integral is the same as the integral of the top surface, and you are going to get a flux of pi a square h leaving the bottom surface. Okay. So, the total contribution of this the total contribution to the integral d dot ds from all the three surfaces can be added up, and for this cylindrical surface that we have considered, the integral of d dot ds will be equal to 3 pi a square h. Okay. Now, let us find this value by a different method. Okay. We have already discussed that integral over the closed surface d dot ds can also be written in terms of its divergence, that is del dot d over the volume enclosed by that particular surface, right. So, let us try to evaluate what is del dot d, and in this case you need to evaluate del dot d for cylindrical coordinates, okay. And if you try to evaluate del dot d for the cylindrical coordinates, you are going to get a constant value of 3, okay. Now, this if you multiply by the volume of the cylindrical element that we have considered, the volume will be pi a square h. Therefore, the right hand side of this fellow, this is the volume, okay. The right hand side of this quantity is actually given by 3 pi a square h. This is rather simple version of finding out this integral of d dot ds instead of trying to use the surface integrals. This integral which reduces which is very simple because the divergence would be constant and it can be taken out of the volume integral, so that the integral can be simplified, gives you the same result as that you would have obtained from the left hand side. In fact, this particular relation we discussed had a name called Gauss's divergence theorem. Gauss's divergence theorem is important because this will allow you to replace the closed surface integral of d, okay, by a volume integral over the divergence of d inside the entire volume. Okay. So, please keep this theorem in mind because we are going to discuss next the topic of dielectrics in the next class. Then you will be requiring to recall this divergence theorem. Okay. You can solve some additional problems and show that this divergence theorem always holds. We will not do that one. Let me go to one additional problem, okay, in the electric fields, and we will then stop discussing the electrostatic fields. Okay. We will stop electrostatic fields and then discuss some of the other things that we want to discuss. Okay. Here I want to consider calculating the electric field of a finite length charge. Okay. I want to consider calculating the electric field of a finite length charge which has uniform charge density of rho L coulomb per meter. Okay. So, the problem here is the charge is lying along the z axis, assume that it is lying along the z axis, and between the points or the planes z1 and z2. Okay. This is the length of the charge. So, let me mark that one separately. Over this, the charge has a uniform charge density, the line charge has a uniform charge density of rho L coulomb per meter, and I want to find the field at point P, okay, away from this charge. I want to find the field at this point P away from this charge, which is defined by r, phi and z. Okay. How do I do that? First question would be, since we have been discussing Gauss's law, can I actually use Gauss law? Okay. Well, unfortunately Gauss's law cannot be used in this case because there is no symmetry along z axis. If you recall, for an infinite lying charge there was symmetry about the azimuthal angle phi as well as there was symmetry about z. You could go up and down along the direction of the charge, but you would not see any difference in the line charge density. However, for a finite length charge there is obviously no symmetry along z, because you can imagine moving from a lower portion z1 and then you keep moving up to the point Z2, right, and beyond that if you try to move, there will not be any charge that is visible to you, there is no charge extending beyond Z2. Similarly, if you try to move below Z1, there will not be any charge. So, the symmetry in Z axis is broken, which is another way of saying that the corresponding electric field will be a function of Z. However, if you go around the charge inside at any point, you would see that the charge would be independent of phi. Okay. For a infinite line charge, the charge would be independent of phi, but in this case the symmetry around the line charge element will be visible only if you are going around a circle on this axis, okay, because at this axis if you keep going around, the fields corresponding from the top portion as well as the bottom portion would cancel each other out and there will be a symmetry along phi. However, in this case if you go at any other point, right, there will not be such symmetry. For example, you can imagine this point P located somewhere up here, and in this case you can keep moving around and there will not be a symmetry phi that you can easily verify. I mean you cannot easily see that there will be symmetry up there. Okay. Finally, symmetry along R, because the field will be dependent on R. Okay. So, let us try to evaluate this one. If you try Gauss's law, we cannot really use Gauss's law as I have said, but instead we can use Coulomb's law. Okay. So, you can use Coulomb's law in order to calculate the electric field. Okay. So, let us use that one. I am going to use Coulomb's law to calculate D and then I am going to relate D and E. Okay. Strictly speaking, Coulomb's law gives you the electric field E. Okay. However, in the medium that we are considering, D and E are related just by a constant epsilon 0. Therefore, I can use Coulomb's law to calculate this electric field. Okay. So, if I consider any point, okay, a small length dz prime and then find the electric field at this point, I can label the angle here as some alpha. Okay. Alpha will be the line, alpha will be the angle that this line from the charge element dz prime makes onto the point P. Okay. There will be this line alpha, there will be this angle alpha measured from the z axis. So, you can now write down what is the D field at point P. Okay. The D field at point P is given by integral from Z1 to Z2, because you would have to go up and down the charge covering from Z1 to Z2. At any point you have the charge rho L dz prime, okay, divided by 4 pi epsilon 0 r square, or rather magnitude of r cube, times the unit vector times the vector at point P, right. So, if you recall Coulomb's law, this would be rho L dz prime r divided by, or rather r hat divided by 4 pi epsilon 0 r square, where r is the distance from the charge location to the field location. This is Coulomb's law. So, if you apply that Coulomb's law to this one, you are going to evaluate the vector distance from dz prime to point P, okay, and that is given by r r hat plus z z hat, okay, or sorry, this is the point at any z that I am considering, whereas the location of dz prime is at some z prime. Okay. So, this would be z minus z prime along z axis divided by the magnitude of this vector. So, you are going to get r square plus z minus z prime square to the power 3 by 2. Okay. I hope that you will remember this from your Coulomb's law. Sorry, there is no epsilon here because I was looking for Coulomb's law. So, this D is actually epsilon E. So, you can actually relate the two as we have said. So, how do I integrate this particular integral? Well, it turns out that I cannot really integrate this to give you a nice analytical expression that I gave you in the case of infinite line charge or an infinite plane of charge or a sheet of charge. So, this is a brute force method that you need to employ. You can solve this integral, or you can evaluate this integral by certain substitution methods. So, you can try z minus z prime is equal to r cotangent of alpha, r cot alpha. So, which implies that dz prime will be equal to minus r cosecant square alpha. You remember that cot is 1 by tan and cosecant is cos by sine, right. So, I hope that you remember these two formulas from trigonometry. So, you can substitute for this. What you have to see is that at the ends where you go, there will be two extreme angles, alpha 2 and alpha 1. Alpha 1 will be the angle from the bottom portion of the line charge, okay, at the below of the line charge to the point field point P, and alpha 2 will be the angle that the line from Z2 to P makes with respect to the Z axis. So, the limits of integral from Z1 to Z2 will be converted into the limits from alpha 1 to alpha 2. You can evaluate this integral and find that D field is given by rho L by 4 pi r. Okay. So, there is a 1 by r, at least that is somewhat a good thing for us, because in the infinite line charge also we had a field going as 1 by r. So, there is a 1 by r dependence, which is nice, multiplied by some cos alpha 1 minus alpha 2. Okay. You will get this one if you evaluate the integral. Okay. By making these substitutions you can evaluate the integral, and after changing the limits you will get this one, plus sin alpha 2 minus sin alpha 1 along z axis. Okay. So, there is a dependency on both r as well as z in the electric field D, as we have written in this particular thing. Alpha 1, alpha 2 themselves depend on the point P. Okay. If you are going to go around the point P, these values of alpha 1, alpha 2 will also change. If you want to sketch the field pattern for this, assume that the charge is lying along here. Okay. If you sketch the field patterns, you will actually see that the field starts to become very thin as you go to the top or the bottom. Okay. So, the field actually becomes very thin as you go here. Okay. However, the field is stronger at the center of the charge, and it progressively goes to lower values as you move away from the charge. Okay. So, you can see that the field is actually very weak over here. Okay. And the field is actually quite going as 1 by r in the middle of the charge. Okay. Again at the bottom also the field will be very weak as you go away from the charge. Okay. So, the field is actually very weak at these points, the field is strong only here. Such line charges are not uncommon. Okay. If you are familiar with precipitation, you will see that later we will discuss precipitators. In precipitators you will see that there is a finite length of wire which is getting charged. Okay. Actually it is getting electrified, but by passing a current, but in the simplified version we can consider this to be a uniform line charge of charge density that is given by the electrification process, how much charge density we are imposing, but the field around this lined charge would look like this. Okay. All right. So, we are sort of closing up on electrostatics now. There is a lot to discuss in electrostatics, we will come back to that, but before that we will have to introduce you to one more vector operation, and then we will review electrostatics, that is we will close electrostatics and then we look at applications of electrostatics. Okay. What is that I want to introduce you to? We have seen two vector operations. One vector operation is called the gradient operation, which allows you to express the electric field as gradient of a potential function. The potential was a scalar field, and therefore, this was very interesting to us because measurements on the potential are more easy to make compared to the electric field measurements. So, you could make measurements or you could specify the potentials in a region of space, and from there evaluate the electric field. Potentials are scalars, whereas electric field is a vector, and you could do that one by two operations. One, an integral in order to evaluate the potential, and from the potential you need to take the gradient, which is differential operation or derivatives that you have to take in order to get the electric field. Okay. The other vector operation that we introduced you to was divergence, and divergence tells you how much flux is emanating from a particular point. So, if the flux is outgoing at a particular point, then it is called, then the point actually has a source. Otherwise, if the flux lines are closing in on a particular point, then at that point we have a sink. So, you could think of a positive charge as a source because the field lines would all emanate from that, and you could think of the negative charge as a sink because all the field lines would converge onto that particular point. Okay. So, we have seen two vector operations, and there is actually a link between gradient and the next vector operation that we are going to discuss.